Now is the time for all good men to come to the aid of their party.
Ryan Reynolds faces Seth Lugo.
Here are some stars of different spectral types. Over here is a mass luminosity relationship. Bibbidi bobbidi boob. Let's see if I can eliminate all that nonsense. So this section is on celestial distances. Understanding the distances to celestial objects, astronomical objects, is critically important to our understanding of the universe. Both our neighborhood, objects in the solar system, or beyond that, stars that are in our neighborhood, and to galaxies farther away, or very far away. In this chapter, we'll begin the discussion of how some of this is done. Solving the distance problem has been extremely challenging, but has brought some very creative solutions, and many of them are just sort of the common sense things that humans have been doing for thousands of years. So let's begin by first just talking about some of the distances we're dealing with. They're standard units of distance. All sort of measurements have an interesting history. So the units we're using are typically within the solar system. We use the astronomical unit, right? That's the average distance from the Earth to the Sun. It's about 1.5 times 10 to the 8th kilometers, which is 150 million kilometers, or about 93 million miles. Sometimes we round that to 100. That number in other units is 93 million miles, or 500 light seconds. How far light travels in about 500 seconds. Another unit of distance we use is the light year, which is about 5.8 trillion miles, or about 63,000 astronomical units. This is a better distance for measuring the distances to stars or other galaxies or something like that. Even when you get to other galaxies, nearby galaxies like Andromeda is 2.5 million light years away. And so sometimes we even look for bigger distances than that. So just briefly, all of these distances get named somehow. And so I'll just talk about the meter for a minute, since it has an interesting history. Originally, the meter was defined as 1/10,000,000th of the distance from the North Pole to the equator on Earth. That was the original definition of the meter that the Europeans were using, I think the French, in the 1700s. And they actually sent surveyors out to measure this distance, doing surveying on the planet, to get a good definition for that. That worked for a while, and then in about 1960, they used this krypton 86 isotope, and used what is that? I'm not sure if there's a typo in that number, but anyway, a huge number of wavelengths in the krypton atom for a long time in 1963. Then in 1983, the meter began to be based on the speed of light, and what they said is the speed of light is exactly 299,792,458.6 meters per second. So light travels 1 meter in 299,792,458.6 of a second. And so this is now the standard definition of the meters. The nice thing about this is, you can send this information to somebody on a different planet or in a different solar system or something like that, right? And they can, you can just say, hey, measure the speed of light on your town, in your place, and then let it travel for this fraction of a second, and that's the thing we're calling a meter. So having standard units of measure is very important. So within the solar system, to other planets and stuff, we've used radar, which is just radio distance and ranging. That's what it stands for. We just bounce light off stuff and wait for it to come back and measure how long it takes. And then since we know the speed of light, we can figure out how far away that object is. It's what highway patrolmen kind of use to measure the speed of your car, those types of things. And so we can measure the distances to nearby objects, astronomically nearby, that way. Things within our solar system, we can measure their distances using radar. And so that's pretty useful. So if you want to do something more sophisticated, if you want to measure the distance to stars, it gets more challenging. We can't bounce signals off stars. They're too far away, and the signal would be too faint by the time it bounced off them and came back. And anyway, they would be their own signals coming out of the stars. The light coming out of the stars would interfere with it. We would never get our signal. So we have to figure out how to measure the distance to stars just by looking at them. And so for nearby stars, we use this technique called parallax or triangulation. And it's a simple concept, and humans have been doing it for a very long time. It's based on the concept of parallax, which, if you hold your thumb out at arm's length and hold one eye, keep one eye closed, and line the other eye up with your thumb, and then line your thumb up again with something across the room, and then you switch eyes, you will notice that your thumb appears to move. This is called parallax. Parallax is defined as the apparent shift in position of an object caused by actually moving the observer, in your case, switching eyes, right? It turns out that you can use parallax to measure the distances to remote objects. It's just a form of triangulation, and your brain uses this all the time. When you have two eyes, your eyes each have a different angle, and your brain figures out how to use that to get a good gauge of the distance to something. And so this is an example of it. With triangulation, you need two viewpoints. These two, I forget what they're called, civil engineering spotters or surveying devices. And then you need a baseline known between them. So you measure this baseline, and then you aim them both at the object you're looking at. And using strings or just little laser pointers or whatever, you can figure out what the angles are in these triangles. And then you can do a little geometry or trigonometry if you're sophisticated and figure out how far away the object is that way. This is the simple basis of triangulation. And you don't actually have to be able to get to the tree, or in our case, a star, to be able to make this work. You just have to be able to take two distant points and get the direction to the object from both points and know the distance between the 2 points, the baseline. And that allows you to determine the distance. For stars, we can do this as long as they're nearby stars. Right? It turns out the farther away you get, the harder it is to do it. If this baseline here is really small compared to this distance to my tree, then my measurements aren't going to be very accurate. You want this baseline to be at least a reasonable fraction of the distance. And so the farther away the trees get, or in our case the stars, the harder it is to do an accurate measurement using triangulation. So when astronomers do this with the Earth to measure the distances to stars, the baseline that they're talking about ends up being the diameter of the Earth's orbit. So let's look at another picture here. Right. So here's the idea. Here's the Earth going around the sun, right? And here's the star whose distance we want to measure. And so when we're on this side of the Earth, we line it up with these stars. When we look at it, this is the picture we get. And when we're on this 6 months later, we're on the opposite side, we see it lined up with these other stars. And we notice that the two pictures, the background stars, look the same. But the foreground star whose distance we're trying to measure is off. And that allows us to determine this angle. The shift in position here allows us to get this angle, and this angle is the important one. It's called the parallax angle. It allows us to determine all the other angles in the triangle. And since we know the baseline here from A to B is the diameter of the Earth's orbit, we can then calculate this distance to this star. So the nearest stars produce a parallax angle of about an arcsecond. Again, this is the parallax angle, this angle right here, the P, of about 1 arcsecond. And so it turns out, with a little trigonometry, which we won't do, you can show that if this P is 1 arcsecond, and this distance is this is the diameter of the Earth's orbit, or about 200 million miles, then this distance here is about 3.2 light years, or what we call a parsec. That's the definition of a parsec. So when the base of the triangle is the Earth's orbit, is the diameter of the Earth's orbit, and the parallax angle is 1 arcsecond, the star is called 1 parsec away. This is the definition of a parsec. A parsec is about 3.26 light years. And so a parsec is another example of a distance that would be useful to measuring the distance to stars. It's not that much better than a light year. They're about the same. Parsec showed up in the Star Wars movie because Han Solo used it as a unit of time. He said that his Millennium Falcon did the Kessel run in 12 parsecs. He was sort of bragging, and that doesn't make any sense because he was using it as a unit of time, and it's actually a unit of distance. So the parallax method works best for determining the distances to nearby stars because the farther away you get, the less well it works. So it turns out we've had several spacecraft that have made parallax measurements. The first one was called Hipparchos, which was named after the famous Greek star surveyor who we talked about in one of the early chapters in this semester. His name was Hipparchus. This was a clever rearrangement. High precision parallax collecting satellite. It was launched in 1989, and it measured the parallax angles and therefore the distances to thousands of stars within 300 light years of us. So in 2013, we launched Gaia, which began operation it was capable of measuring to a few 10 millionths of an arcsecond. Now, an arcsecond, I think I said up here before, I didn't say it, but I wrote it. Or maybe I didn't. Hang on. Well, I thought I did. Here it is. An arcsecond is 1/3600th of a degree, right here. This angle is roughly what is made by a quarter at a distance of 3 miles. That's an arcsecond. So if somebody holds up a quarter 3 miles away from you, the angle that makes from one edge of the quarter to the other edge of the quarter is about an arcsecond. So this spacecraft, Gaia, can measure a few 10 millionths of an arcsecond. So take that quarter and divide it into 10 million pieces, slices, and that's how tiny an angle this Gaia can measure. And so by 2022, it will have measured the positions and distances for about 1 billion stars, spanning about a third of the galactic disk. It's an astonishing achievement. And so this is going to give us a really good database for the distances to stars. It is currently giving us that. So this next section is about, so explain why satellites give more precise distances than ground-based systems. Well, this is kind of what you might expect. There's no twinkling of stars. There's no atmospheric interference. Every star you look at through a telescope is a little bit fuzzy and twinkly because the atmosphere messes up its motion. This doesn't happen in space. In space, every star looks like a point, and there's no interference by the atmosphere. There's no blurring or twinkling or anything. And so you get much better results in space than you do with ground-based systems. Discuss astronomers' efforts to study the stars closest to the sun. Parallax measurements have been made for the stars within about 10 parsecs. There are 357 known, so this is about 32 light years, within 32 light years of us. There are 357 known stars in this region. Keep in mind that, they could still find some more, which tells you how dim they are. They're hard to find because some of them are very dim. Of the 357, 248 are red dwarfs. Again, we talked, they're more small stars than big stars. So it's about 70% of them are red dwarfs. The nearest stars are Alpha and Proxima Centauri, which are 4.4 and 4.3 light years away, respectively. And so that's for sort of nearby stars. And it turns out that there's another group of stars that are useful for measuring distances too. So if you get past parallax, so we'll never be able to use parallax, or I shouldn't say never. It's unlikely we'll be able to use parallax to measure distances to stars in other galaxies. And so to measure distances to things that are farther away than parallax gets us is more sophisticated, is trickier. But it turns out that there are variable stars that help us with this. So stars, when they leave the main sequence, when they're done fusing hydrogen, they sort of move into that red giant phase in the upper sort of right of the HR diagram. And they get cooler and brighter. They get cooler and larger, so they're more luminous. They're less luminous because they're cooler, but they get much bigger, and so they end up being more luminous. And these stars can be as luminous as 100,000 suns or something like that. And so when something is super duper bright, you can see it really, really far away. And these variable stars often have an oscillation to their brightness. They get bright and dim and bright and dim, and they call it the period. And so it turns out that their luminosity and their period are correlated, and so you can watch a star get brighter and dimmer and brighter and dimmer. And even though you couldn't normally look at a distant star and tell what its luminosity is, because its luminosity is sort of its absolute brightness, is its power output. And, a 100-watt bulb, if it's, twice as far away as a 25-watt bulb, will look the same. And so you can't tell the luminosity of something unless you know more about it than just how it looks from where you're standing. And it turns out that with these variable stars, we can look at the oscillation, the rate of oscillation of their luminosity as they get brighter and dimmer and brighter and dimmer, that the period correlates with their absolute luminosity. And so we can get their luminosity by looking at the way they brighten and dim. And we refer to these as sort of standard candles, that is, objects whose luminosity is known. And when you know an object's luminosity, right, if you look at this equation, again, we're not going to solve it, but we can just talk about the algebra of it. The brightness is just how something appears. You can always measure the brightness of anything you can see. The thing you don't know generally is the luminosity. But for these variable stars, you can look at the way they brighten and dim, measure the period, and that correlates with the known luminosity. And so then you can get these two things. The only other thing that's unknown is R, and you can use algebra to get the distance. And so variable stars allow us to measure the distances to them because we've got other clever tricks for determining their luminosity. And so measuring brightness is easy. You just aim the telescope at it. Getting the luminosity is trickier, but you can get it. You can do it potentially off an HR diagram. But the best way to do it for these variable stars is to look at their period of oscillation, and that correlates with their luminosity. Often these stars are very bright and allow us to see them even though they're extremely far away. Henrietta Leavitt discovered the period-luminosity relationship. She's the one who figured this out, the time it takes for one cycle of brightness, that it tells what the luminosity is. And so we can determine the distance R from these equations, as I was saying a minute ago. There are two of these types of stars. One are called Cepheid variable stars, and one is called RR Lyrae. And most of the RR Lyrae, by the way, Cepheus is just the constellation the first Cepheid variable was seen in. And Lyra was the first one that one of these stars was seen in, and so they're called Cepheid variable stars and RR Lyrae stars. And they're very useful in determining distances to objects that are very far away. all our light rays have about the same luminosity. And so once we know that's what type of star they are, we pretty much know what their luminosity is. And so we've even used Cepheid variable stars to look at the distances to other galaxies because they're so bright they can be seen in a distant galaxy. So that's what the variable stars are used for. So we can use parallax to measure the distances to nearby stars, and we can use variable stars, the Cepheid variable stars and our Lyrae stars, to determine the distances to faraway stars or to faraway objects.